we're going to do in the next 2 lectures is actually, I would say, the most dense mathematically portion of this course. And we are mainly using tools that are connected with statistical mechanics, quantum statistical mechanics. Now, what we will be doing is calculating the heat capacitance and the magnetic moment of solid-state systems, which at the moment we will ignore the fact that they're on a lattice, just due to the fact that we have free electrons closed in a box, which is the 0th level model of a metal. Now, why do we do it? Why do we bother to do non-trivial calculations that need some attention and not run immediately to the ideas? Because actually the ideas, at least for the heat capacity, I already told you. Well, there are a few reasons. One of them is basically, as physicists, working either in research or in industry or algorithms or whatever, you run into complicated calculations, and you should not be afraid and see how it's done stage by stage. It involves mathematics, not more than you have been introduced in the previous courses, so that's not terrible. Moreover, these 2 quantities are some of the most important quantities that we have in solid-state physics. Heat capacity gives us a way to approach properties of metals and measure them without really knowing what's happening for individual electrons and or phonons and things like that. We can deduce some very general properties out of the behavior of the heat capacitance. That's historically, that was our first approach into quantum mechanics in solid state. These things were started by the guy who started everything, Einstein, and continued by a whole generation of physicists, more or less finishing up in the 50s and 60s. And these techniques are still used till today in some problems in solid-state physics. Second, the second property that we'll delve into is the magnetic moment. And magnetic moments, if you're not convinced till now, has something to do with technology a bit more than just sticking things to your fridge door. All your memory technology is built on magnetic properties. So it's important to know and understand what determines it. At least the part that comes directly from the electrons. Okay, so what we're doing today is the heat capacitance. Yeah?
What about conductivity? We saw that the model was incorrect.
Right, but for conductivity we need the lattice properties. And they are completely determined by the lattice properties. Some of what we're saying here is also dependent, especially the magnetism, but we'll see. And to do that, we have to do one step before it, which is the Bloch theorem, which tells you how a wave function of an electron in a lattice generally looks like. Once you have this theorem, We won't go and calculate for each type of lattice what is electronic properties. We'll have some very general properties that we could understand the behavior of particular metals once you're giving me the lattice structure. After we do conductivity, we'll get to the pinnacle of modern electronic technology. What the hell is a semiconductor and why is it so important? Okay, so back to heat capacitance. We have seen that basically the energy per electron at T equals 0 is not sure that I use this definition, but let's use a simpler one. Which makes a lot of sense. We have energies between 0 and E. We have more energies at higher energies for the simple reason that we have more states there. So the average is not a half, it's larger than a half. I'm not sure that you could have pulled out the 3/5 out of this simple argument, but once we do the calculations, that's the result. This is not useful for heat capacitance because heat capacitance asks what is the influence of temperature on the internal energy of the material. And here we have no temperature. We don't have even a way to calculate the temperature. Okay, so what was the basic assumption that we had in the last lecture to calculate it? We assume all states up to E Fermi are occupied, all states above are 0. We did the integral and got this result. What should we change? Well, temperature, of course, but what should we do in our calculation to incorporate the temperature?
To use the Fermi distribution.
Right. The occupation of each state is not 0 or 1, depends on temperature. Everything else is the same. This small change puts us into mathematical difficulties, but conceptually it's very clear. Instead of having an occupation of a state, Fi, that was our assumption at T equals 0. Okay, so I have T in the occupation, so in principle I know the roles that temperature plays here. This is the occupation for fermions. well, electrons happen to be fermions. Hope that's not news for you.
Greater than E Fermi.
Hmm?
A probability to be greater than E Fermi. Yes, not zero.
Correct. Okay, so first, this expression is ugly, but I have another problem. I have an additional parameter here that I don't know. Mu. Now I have a conceptual problem with mu. I'll mention it and later ignore it. Why? Because historically it was not interesting, but nowadays in more modern experiment it could be important. The concept of mu in statistical mechanics, from where does it come?
An exchange of particles.
It's the grand canonical ensemble, and what specifies a grand canonical ensemble is the fact that it exchanges electrons with its environment. Now, if you think about it, a piece of metal that sits somewhere in the room doesn't exchange electrons with the environment, has no source of electrons.
But the free electrons exchange with
the air,
bounded electrons.
very little, actually. Free ions in the atmosphere, usually in a regular room atmosphere, is not very.
I mean ions in the metal.
No,
But what we are talking about is not exchange of electrons, it's exchange of occupied states. So different states can be occupied or unoccupied, and that's the number we're talking about.
no. That's exactly why I'm talking so much about that. This is a misconception.
What we learned in statistical mechanics.
Okay, so let's relearn statistical mechanics. You have three ensembles. This is not our material, but as a physics, someone who finishes graduate physics, you're supposed to sing it in your sleep. A microcanonical ensemble. This is a system that is insulated both for energy exchange and particle exchange. Meaning that if I have an energy and number of particles, it's supposed to stay such forever. So what statistical game can happen in this system? Only I can move between states that have equivalent energy. That's the only game I have. It's not this e to the power, the Boltzmann distribution for classical or whatever, or this distribution for quantum mechanics. No, the only question is how many states I have with exactly the same energy, because the energy is conserved and you can't exchange it. And between those states you have the same probability. So the probability is very simple, 1 over the number of states that have this energy. End of story. Nothing more, nothing less. There's even no concept of temperature for such a system. For the simple reason, I can't change my energy, and temperature gives you some probability of finding the system at a given energy. The probability is 1 to find it at the energies that I started. As a cute example, the energy of the whole universe. If I'm taking a naive look that the universe is all that I have, the energy is fixed. Can't ask the question, what is the probability of finding the universe at some energy? Whatever that started, that's what I have. Okay, so I'm in touch with some heat bath that has some energy and some number of particles. Usually, I assume, well, otherwise I shouldn't call it a heat bath, I should call it another system, that the energy and the number of particles in the bath is much, much larger. Add a few large there, it's tens of orders of magnitude usually. And it can exchange energy, which means that I can't say that the energy is constant, only that the sum of the energies of the bath and the system is constant, and since the energy of this bath is so much larger than the energy of the system, I don't even bother to put this constraint, because small changes, any change here would be an extremely small change here, and therefore can neglect it, but this is constant. But I have no exchange of particles. And not equal, but the same thing, n and n prime are cons. Same picture. But here both exchange of energy and exchange of particles and therefore the const is just on both of them. Okay. The fact that I have a constant energy but it can be exchanged created this parameter t. What is this parameter t doing in this game? It sets an average energy of E. Could be average because energy can be exchanged. Here I have two parameters, t and mu. T sets the constraint on the energy, mu sets the constraint on the number of particles. Now, if I'm measuring the heat capacitance of a piece of metal, it is not necessarily connected to a bath of other electrons. So I should have worked in the canonical ensemble. It's a nightmare. So people assumed, well, it's not so important. Let's take the easier path from the point of view of mathematics and work in the grand canonical ensemble. Remember, this neat description exists only for the grand canonical. Clue, you have here mu and t. If you didn't have mu or t, you should have put a strict condition on the number of electrons. But since the number of electrons is so big, so a small change won't change the properties of the material, therefore we're moving to grand canonical. There is an additional reason why it's not so terrible, because a lot of experiments on metals are done also when they are connected to a battery through wires. And then you have a bona fide source of electrons, and then it's not some mathematical convenience, it's a good description of what happens if it's hooked up to some battery or some other metals that can transfer electrons to it. Why am I going through all this? 30, 40 years ago, I would just say, well, we're using grand canonical for convenience, and it doesn't make a difference. Nowadays, you have a whole building that's called the nano building, and there the number of electrons are not 10 to the 23rd, but perhaps such a small metallic particle that has 10 to the 4, 10 to the 5 electrons. In this case, you have to stop and ask, well, using a grand canonical description, does it make sense? Does it change my results? And personally, I was working 2 decades ago on magnetic properties of such small clusters, and it makes a difference. You cannot just throw in grand canonical and forget about everything else, which you see in experiments. So this lecture will be all in the grand canonical assumption, but keep in the back of your minds, especially if you're working on nanoparticles, adjustments may be needed. If you're using the grand canonical ensemble, stop a moment and think, is it okay? Will it make a difference? Sometimes yes, sometimes no. Okay, so we need to find out mu. How do we find mu?
Setting in a constant number.
At the end of the day, I want the sum of Fi, the average number of electrons. It's average because it's a probability. Want to find mu, you have to solve this integral. I'll use U not to get confused. I'll use E as an integration constant, and I don't want to get confused. It's other. So once I find mu, I go here, multiply the probability of a state with the energy of the state, sum up over all states, I get U. Once I have U, depends on T, I can perform a derivative, I have CV.
Should the first summation include the NI? If I is only the probabilities.
Yeah, and if I know the probability of occupation of each, look on this, always mentally stop if something looks complicated, stop and look what happens at t equals 0. What do I do here? If the state is occupied, so the probability is 1. So I have a lot of states that have probability 1, and each one has an electron, or actually I should be more careful. Spin. And we'll see for magnetic behavior, it's very important to remember that we have 2 occupations per state. So once we do this, we have the number of electrons. More, and this gives you the energy. Probability times the energy, sum over all the states. That's it. So actually this is statistics. The only physics that comes into the game is the terms that we introduced for the probability, which is probability of of fermions. Good. Since summing is hard, we'll do our first approximation. We'll move to integration. Since K gives me an indication of all the states, you remember that we did it in the previous lecture. We have here the integrals that we should perform. What happened to the 2? We had here 8. Now we'll introduce the concept of density of states. Remember, what am I doing here? At the end of the day, I have here a sphere. Tell you in secret, this assumption doesn't hold once I have a lattice. But for a lattice, I have here a sphere if I wipe out the discreteness. Okay? And what happens for a sphere? We have here symmetry in theta and phi, and only K norm is in the game. But K norm is connected with an additional very intuitive physical quantity, which is energy, because energy is equal K squared up to constants. So we want to transfer our vector type of integration or three-dimensional integration into one-dimensional integration over energy. So it's just a change of variables, nothing more. So we know E What happened here? Nothing beyond change of variables. Okay, DE is connected to, I had here, first of all, the theta d phi gives me 4 pi, taken care here. So instead of 4 pi to the third, I have just pi squared. That was the theta and phi. Okay, what do I have here from dk? K squared dk, right? Okay, one of those k's is swallowed by this term, the second remains. This guy, simply this guy. And this guy requires a name. Density of states. Tells you how many states do I have at any given energy. What we see here is that the number of states increases as the energy increases. So the sphere becomes larger. But pay attention, this depends on dimensionality. Again, 40 years ago, I wouldn't have to emphasize dimensionality because, what do you mean? All solid-state systems are three-dimensional. Nowadays, that we regularly manufacture 2D and 1D systems, even use it in our technology, you have to pay attention that if dk was for a two-dimensional system, you can see that I would have, instead of k squared here, only 1 power of k, which would have been swallowed directly into this one, and the density of states would have been constant. So very generally, can guess what will be the behavior in 1D.
1 over the square root of.
Yes, because then I have no contribution to k here. I have to somehow correct this k. K gives me a square root of k in the denominator. So, as we will see, the properties of heat capacitance depends on the form of the density of states. It's clear already from here, which means that it will depend on dimensionality. Okay, so that was general discussion of what happens to the density of states and emphasize that it depends on dimensionality. And just to give us a scale, the density of states for three-dimensional systems at the Fermi energy just from the definition, and we can write it down also as just insert the definition of the density of particles. So we have two integrals. Write it this way. Okay, in steps Sommerfeld and gives us a approximate solution to it at low temperatures. You probably have heard of Sommerfeld. Where? The most known.
Bohr-Sommerfeld relation.
Bohr-Sommerfeld description of the hydrogen atom. He incorporated relativistic correction to Bohr's quantization in the old quantum mechanics. Okay, so
לא חסר אפסילון במקרא מימין, כאילו G אפסילון, F אפסילון. אם זה שווה ל-U, אז לפי מה שאמרת בשמאל. ואז זה מסתדר גם עם ה-K. DK, יש אנחנו עושים את זה בספרי, זה K בריבוע DK. צריך שמתרגם לאפסילון נוסף.
Oh, sorry, I wrote here. So. Okay, why small n? Another point that I didn't emphasize.
Because you're missing the volume.
Right, because if you remember, you had here L2 divided by L to the power 3, or L to the power of the dimension. Okay, so basically we have here a family of integrals for which we have to calculate this integral, where h is GE for n, E times GE for U, for the energy. So again, small u divided by volume. Okay, so Sommerfeld came up with the idea to write h of E as a derivative of another function it's not clear why it helps, but can do it. Okay, let's see what it helps.
Integration by parts.
Right.
That's associated with the group of velocity of the wave, right?
Could. But at the moment it's just a general definition of any function that is multiplied by the quantum fermion probability. Well, of course, the moment I said approximation, it will claim that something here is small. But let's wait a minute.
Shouldn't it be from 0 to infinity?
Yes, but it will make our life easier to take it from minus infinity. Why doesn't it matter?
Shouldn't we just half it afterwards?
Because all interesting changes as function of temperature only occur around the Fermi energy. So whatever happens previously is not very interesting. That can't change with T. If I take my system and say instead of states starting to fill up at 0, I say this ridiculously sounding assumption, they fill up till minus infinity. Of course, as if I calculate the number of particles, it will make a huge difference. But if I ask what is the change as function of temperature, makes no difference. Because states very deep inside cannot change as function of temperature. That's the advantage of working in the quantum world. Because in classical, of course, if I'm more negative in energy, I have a higher probability to sit there. But okay, I've deleted it. But for the Fermi-Dirac statistics, it's 1 no matter what's happening. So it doesn't matter. So it gives you a way to simplify your integrals. So I wrote it down as an integral in parts. And this is the main point in this whole exercise. Why? F is a function that is about 1 or 0 everywhere except around the Fermi energy. And if the temperature is small, the region where that happens, this value is non-zero, is quite small. No, I'm not there. So it gives us a very specific region where everything happens. So I don't have to worry about the minus infinity, I don't have to worry about the infinity, I'll have a strict small region where everything happens. What did I do here? If everything happens around mu, then all that interests me is the behavior around mu. So I take a Taylor expansion around mu. Okay, back to my integral.
אתה בעצם אומר שכל הסכימה של האיברים האי-זוגיים מתאפסים ושם כל הזוגיים.
I throw out the odd contribution because they are the same, they are odd around the point of mu, therefore I can throw them out. I'm left only with the even contributions. So what did I do here? Nothing beyond sticking in this expansion of k and putting in the terms. Okay. Now, let's stop a minute from being very general and actually introduce f into this game. And to make life, or at least notation, a bit more condensed, and replace e minus mu over kbt, which appears in the exponent, with another variable x. So, looking on the second term, okay. Looks terrible. But one thing is somewhat helpful. This doesn't depend on t or on x. You can pull it out. All this scary, but not in the integral. And this guy okay. Okay, so I have this lovely integral to perform. So I'm writing only the integral. Over 2n, 2n factorial ex x plus 1 word. I rewrite it as what did I do here? Just divided by e to the power x, the upper and lower part. What the hell do I do with this? So,
1 over z minus 1 over z.
hmm?
1 over z minus 1 over z.
In a moment I'll go into the complex plane, but I need still something to stuck in my throat, right? Okay, I want to write a similar integral, which will see the connection. Why is this better? Or what is the connection between those two? let's do a Taylor expansion with K. Okay. But next, so we won't get confused with the n there, let's write n. Summation is good. Why? Because at the end of the day, we'll have to sum up here. So doing this integral will give me both the integral and the summation in one swoop. This is beautiful. Need someone like Sommerfeld to see this behavior. Worst thing once in your life. So, instead of a summation and some ugly integral, once I solve this, I'm through. Now, what do I see here? This screams of a complex integration. Why?
Of the poles in the...
I have here poles, and I have here a trajectory that will go to 0 anywhere in the complex plane. Because ik times any z that is not real gives you a minus here from the imaginary part and kills the contribution of the trajectory. So this is a very nice example of doing integrals in the complex plane. Okay, so let's do it. Okay, this is my integral. I'll close it above. So I'll have a positive imaginary contribution at infinity, of course. This will give me a negative exponential, will kill the contribution of this part, will leave me only with this part. Life is good. That's why I put to minus infinity a few steps ago. Not I, Sommerfeld. Okay, now we have to just find the poles in the upper half. Okay, where are the poles? Any time that you get here or here minus 1, right? Where do you get minus 1? I pi 3 I pi
5.
and so on and so forth. So all I have to do, all in parentheses, is sum of the contribution of these poles, and I'm finished. So, of course, the point that makes my life hard, it's not a it looks as a complicated pole, right? But wait a minute. Let's write it down a bit more carefully. That I can always do, right? Why can I do that? I to the I. E to the I pi is minus 1, so I'm writing minus 1. Okay, still the summation over all these poles I will have to do this treatment for each one of them. Next Sommerfeld trick. I won't close it this way. I'll close it in a trajectory, in a path that has only one pole. What is this path?
Origin.
Two straight lines. Why? This guy is I. This guy is just I e to the power minus k 2 pi k. K times I. And closing up, it's this minus this. Infinity doesn't contribute. So I don't even have to go and treat all the other poles. So not always you go in the textbook close it at infinity. Sometimes easier to get rid of all these additional poles and stay with one. So instead of, so we can calculate what is I minus I to the power minus 2 pi ki. So let's sum up what we have here. what do I have here? The path is the contribution of the path and the contribution of one residue, but it's a double residue, and therefore I have a derivative there. Okay, so I go and do the calculation. Let's first of all finish the right side. So I is equal to nothing beyond dividing by this term and identifying
זה לא סין, כאילו אחרי,
of
ואז
course.
השתיים הולך. שתיים למעלה גם, כי זה
Essential and
כי סין.
yeah, no needing for the two. Correct. Okay, so after all this exercise, going back to here, and we end up with some numbers. At the end of the day, all this complicated exercise gave me some numbers. So if you're really in need of more numbers, go and continue the expansion here. So, we are left with powers of t, dependence of the function h, and some numerical constant. We worked very hard to get, but at the end of the day is just a numerical constant. Okay, so after this tour de force in mathematics, we're back to physics. Let's put in the two h's that are of interest to us. See what we get. For the more mathematical inclined people, mathematicians have shown that this A of M or N, whatever you want, is connected to other known numbers in mathematics. Which is a Bernoulli number. It has also a connection to the zeta function. Anyone who's interested can check in Ashcroft. Okay, but for us, at the end of the day, it's a number. And that's all that interests us. Okay. Let's write the expression for our integral. If you have forgotten, we started from h e f e dE, and we got okay, explicitly for the energy. So, what is And okay, let's stop a minute and look on n and after consider u. I just such that what was h for mu? Remember, mu, the calculation of n was GE times FE, right? So H is GE. So I look at my expression. This is the first term, right? H is G. Exactly what's written here. The second expression is the derivative. Okay? Derivative. Okay, written here. What happened for u? Okay, here H is E times GE. So in the first term, which is this guy, what's written here? And the derivative, you have a derivative on G times E, but E is at point mu, so I write down mu. And derivative of E, which is 1. So I'm left with this guy. So I just wrote down the expressions for U and G, sorry, for U and N, according to the description here. Nothing more, nothing less. Okay, I'm still in somewhat of a problem. And I have to calculate the expression, the integration till mu, and get n, which determines mu. So how do I cut through this Gordic knot? I assume that mu is not far from EF, which is okay as long as the temperature is small. Right? It won't push it much. So, anytime I have, doesn't matter if it's GE or epsilon times GE, I expanded in mu minus EF. Okay, finally, let's say something about what is the behavior of n as function of temperature. so I'm going back to this integral, and this is broken up to two parts, according to what's going on here. Third term. And what is this guy? No temperature, integral over the occupation times the density of states.
What?
No. Number of density of electrons. We did it at
Number of electrons.
number divided by volume. You remember that we threw out the L's to the power 3. So this is simply n. So we end up, and here we'll stop, with the chemical potential. Okay, so mu regresses, goes back proportionally to t squared and these terms, but these terms I know how to do. Just perform a derivative on the density of states, insert EF, divided by the density of states at Fermi energy, so I can write it down. So just insert the results, and the important thing is KBT is divided by E for me. So the answer, when can I do all these lovely gymnastics and assume T is small? As long as KBT is much smaller than E for me. Okay, now what is left? As I said, I'll stop here. Insert it in U also, and get the heat capacitance. That we'll do in the next lecture. כן.
שם אמור להיות ב7 פאי חלקי 360 במקדם של הפייבול ברביעית. הפאי הוא גם ברביעית, לא?
כן, בהחלט. להיסטוריה. ואתם כל החישובים האלו יש באשקוף, אז אם אתם לא פתוחים באיזה פקטור פאי או 2 או שאני יודע מה, יש את זה. בסוף היום כל מה שאתם עושים זה משתמשים בטבלה של ה-A'ים ומכניסים לפיתוח. ומעבר ל-T ברביעית לא תגיעו אף פעם בה. לא יהיה לכם צורך להגיד.
כמה זמן יכול. אני לא מספיק.